We rely on measurements for absolutely everything, right? I mean, from engineering to medicine, it's the bedrock. But what happens when the very tools we use to measure reality start, well, secretly lying to us? Welcome to This Explainer. Today, we're going to trace the genuinely fascinating progression of a research program that tried to map out the fundamental geometry of physical systems, hit an absolute brick wall, and was forced to completely reinvent how it measures the world. It's this incredible story of evolving from just asking what exists to rigorously questioning what actually survives change. The whole program kicked off with this beautifully ambitious, almost philosophical question: what can persist in sentience? Basically, when everything around us is in a constant state of flux, what fundamental structures actually stay exactly the same? But as the researchers tried to turn this into hard operational science, they hit a massive snag. They quickly discovered that answering this required them to confront the deep structural limitations of measurement itself. They weren't just measuring physics anymore, They were suddenly forced to audit their own scientific lens. So here's our chronological roadmap for today. We'll be looking at Phase A, measuring systems, the crises and pseudo-replication, entering the well, cross-domain variance behavior, Phase C, measuring measurements, and finally the priority queue. All right, let's start right at the beginning with Phase A, measuring systems. In those early days, Phase A, the researchers were honestly just trying to measure physical systems directly. Their main focus was on something called representation stability, basically seeing if certain physical domains were inherently more stable than others when they tweaked the math. But over time, their focus had to zoom out drastically. They moved from measuring the systems themselves in Phase A to Phase B, which was measuring their measurements. And now they're approaching Phase C, where they actually study the structure and uncertainty of measurement behavior itself. So how did they get pushed this far back? Well, actually, it wasn't by choice at all. Which brings us to the replication crises and pseudo-replication. This whole evolution was triggered by a really severe internal replication crisis. As the team expanded their audits to new domains, these massive, glaring contradictions started popping up. Single-instance results that looked absolutely brilliant at first suddenly just fell apart. They were forced to stop and ask, why are these early metrics failing? How could metrics that looked so solid initially yield completely incompatible values when they expanded the domains? Take a system called Rayleigh-Taylor, for example. An early audit gave them a highly stable value of 0.001. But then, a later replication audit yielded 0.120. That is a massive discrepancy. The metric was literally breaking right in front of them. So the research director dug in and discovered some major methodological failures that were totally corrupting the data. The first big one was pseudo-replication. Think of it like taking 5 different pictures of the exact same cake and claiming you baked 5 cakes. It creates this false illusion of replication because you're just sampling one trajectory over time and pretending they're independent worlds. They also hit protocol drift, where changing their analysis methods midstream was causing contradictions. And finally, the temporal warning, which showed that a system's stability actually fluctuates depending on exactly what point in time you measure it. I absolutely love this quote from their internal archive because it perfectly captures the project's ruthless new skepticism. R squared equals 1.0 is suspicious, not triumphant. I mean, normally a perfect correlation, an R squared of 1, means it's time to pop the champagne, right? But here they completely stopped celebrating. A perfect correlation became a huge red flag that the metric was secretly just measuring a simpler artifact, or was basically defined by the exact thing it was trying to measure in the first place. Okay, let's move into entering the well. To combat these inherent biases and basically stop fooling themselves, the researchers created what they called the well. They completely stopped relying on internal simulators and started pulling in data sets from genuinely independent, radically different physical worlds. We're talking everything from chemical reaction diffusion in Gray-Scott to fluid convection in Raleigh-Bernard, and even a highly complex plasma simulations like MHD. These are totally different physics, governed by completely different research communities. And look at the difference here between the unconstrained domains and the constrained ones. When they threw their metric at the MHD plasma dataset, which is a system packed with intense magnetic and topological constraints, they totally expected chaotic results. But instead, it was ultra-stable. The evidence strongly suggested that strict physical constraints actually act to stabilize the measurement behavior itself. It was a real light bulb moment. Which leads us right into cross-domain variance behavior. This realization brought about a really pivotal shift in how they analyze data: variance decomposition. Instead of just looking at the final average score of a metric, they realized they needed to deeply understand the cross-domain variance. By breaking down and separating the data, they could finally see if a measurement was changing because the physical trajectory itself was different, like a truly independent world, or just because time was passing within the exact same trajectory. And when they ran the numbers on this, they found something, honestly, stunning. If you look at the absolute scores for Gray Scott and Reilly Bernard, they're vastly different. Gray Scott is roughly 20 times larger. But look at the variance ratio between the within trajectory and between trajectory variation. They are almost perfectly identically matched at around 1.04 and 1.05 times. And this brilliantly illustrates the research director's ratio warning. It proves that you can no longer just organize these domains simply by their overall scalar magnitude. The variance structure itself might be a universal signature, even when the absolute scales totally conceal it. And the reason this matters to us is that it proves that similar behavior on the surface absolutely does not mean the underlying engines are the same. All right, that brings us squarely into Phase C, measuring measurements. To survive this new phase, where the actual object of study is the distribution and behavior of the measurements themselves, they had to adopt some rigorous new philosophical foundations. First, a variable is explicitly not the same as its measurement. Second, disagreements are archived, they are never deleted. And incredibly, they realized that zero is scientifically meaningful. When they found a literal zero in an acoustic scattering test, it changed everything. Instead of treating it as a glitch or a failure, they treated it as a profound discovery. The anomaly actually provided way more value than a confirmation. The whole program now operates under this strict, profoundly humbling mandate. Every explanatory layer is provisional. They intentionally avoid prematurely promoting any of these survivor metrics to foundational truth. In this hyper-rigorous culture, the very second you think you found a universal variable, you freeze it, you audit it, and you actively try to break it. They advance by constantly identifying and then transcending their own foundations. Let's take a look at the priority queue and their next steps. Because they strictly refuse to generate new theories until their measurement protocols are totally bulletproof, their roadmap into the future is incredibly deliberate. Step 1, replicate active matter. Step 2, fully compare those cross-domain variant structures. Step 3, integrate that massive, constrained MHD plasma dataset. And finally, step 4, introduce genuinely external, independent human observers just to see if their findings actually survive outside the bubble of their own lab culture. To leave you with a fascinating final thought straight from their archives, consider this question that drives all their future work. Does the relationship survive change or only the measurement? It perfectly highlights the absolute heart of their current work, pushing way beyond what is just measured and stepping into the unknown. It's a question that forces us past the illusion of our own data, making us ask what is truly real. Thanks so much for joining this explainer, and remember to always keep questioning what you measure.